Hi, my name is Louis, and today I will be talking about efficient algorithms and new characterizations for CSP sparsification. And this is joint work with Sanjeev, who's at Penn, and Madhu, who's also at Harvard. And so to start, I'll just talk at a high level about what exactly sparsification is. And so typically in the sparsification, you're given a class of queries, which I'll denote here by capital D, and you're given some object X. And now the goal is to somehow compress this object X to a much smaller representation. This is what we call sparsification, such that for every query Q in your class of queries, the response to the query on your sparsified, compressed version of the object is within a 1 plus or minus epsilon factor of the original response to the query Q on your starting object, capital X. And so in a typical sparsification context, the number of queries that we're interested in is exponentially large in the starting object size X. Nevertheless, because we allow for this little bit of error, it's only a 1 plus or minus epsilon approximation of the response to the query, it turns out that sparsification can often be done with very non-trivial savings in like the bit complexity of the object. That's to say that this error allows for much smaller representations than is typically possible with exact compression of the object. Nevertheless, when you compare it with something like lossy compression, while it might not get the same space savings, it turns out that having this 1 plus or minus epsilon multiplicative approximation is a very strong quantity in terms of the similarity that it guarantees with respect to the original object. So in this sense, sparsification is kind of the best of both worlds. It allows for very non-trivial savings in the space complexity, but it also allows for very strong guarantees on the similarity to your starting object. And lastly, when we talk about sparsification, we often have this extra requirement that your sparsified instance is in fact still an instance of the same structure. And so what this means is that if you had an algorithm which works for your original object X, it should still work on your sparsified version, sparse X, because it will be still an instance of the same global structure. And so to kind of make all of this concrete, one of the most common settings in which people look at sparsification is in the context of graphs. And so here, you're given a graph G with vertices V and edges E. And one way that you can define sparsification, right, one way to define the class of queries that we care about is by looking at the cut sizes of this graph G. And so to define the cut sizes, we look at every single possible cut in the graph. And so here, a cut is just specified by a subset of vertices, which I denote by S. We then let delta of S be all the edges that go from S to V minus S, right? So in another way, delta of S is all the edges that are leaving the set S. We can then define the size of the cut defined by the set S, and I denote this by W of delta of S to be exactly the weight of all the edges that are leaving the set S. Right? So you look at all these edges that are leaving S, and then W of delta of S is just the sum of the weights of all of these edges. And this is enough to define something that we call a cut sparsifier. Right? So if you're given your graph G in a value of epsilon in 0, 1, we say that a subgraph H of G is a 1 plus or minus epsilon cut sparsifier of G if simultaneously, for every single cut in the graph, we have that the weight of the cut in H is within a 1 plus or minus epsilon factor of the weight of the cut in G. And so one way to see this is, to look at these examples on the bottom. So on the left, I have a graph G. And on the right, I have what I want to argue is a cut sparsifier of this graph G. And so I've denoted this by H. And so as an example, if we looked at a set S here, defined by these 3 vertices on the left, you can kind of see that the weight of these edges that are leaving S, and in fact, in this example, all the edges are leaving S, the weight of these edges in G is approximately the same as the weight of the edges in H, right? Even though there's more edges that are leaving in G, we've increased the weight of the edges in H to kind of compensate for the fact that there's fewer edges in H. And so in this sense, we can argue that the actual cut sizes themselves are approximately the same between the two graphs. Again, cut sparsification is a requirement for every single cut in the graph. And so here we can look at a different cut. So here now S is just these like bottom left two vertices in the graph. And again, we'll see that even though there's more edges that are leaving in G, the weights of the edges in H are increased in such a way that the actual weight of the cut size defined by this set S is approximately the same between the two graphs. And so in a pretty amazing sequence of works, Bencher and Carter in the 90s showed that every undirected graph G has a 1 plus or minus epsilon cut sparsifier that preserves O tilde n over epsilon squared edges, where here the tilde is only hiding a logarithmic factor in n. And so it turns out that this has many applications to sublinear algorithms, because it's a very powerful statement. It's saying that even if you start with a graph that has as many as order n squared edges initially, you can always compress it to a graph which retains essentially order n, O tilde n edges, while still preserving all of the cut information in the graph to a 1 plus or minus epsilon factor. And so naturally, this has applications to, for instance, dynamic streaming algorithms, where having this approximate information of a graph is very important. Well, you additionally have the constraint that you can't afford too much space to actually store the entire representation of the graph. And kind of motivated by this applicability to sublinear algorithms, in recent years, people have instead shifted their focus to understand what other combinatorial objects are amenable to sparsification. And so far, kind of the most abstract notion in which we study sparsification is in something called CSP sparsification. And so in CSP sparsification, again, the object of study will just be a CSP, or a constraint satisfaction problem. And so here, the CSP itself is specified by 4 different things. So first, you have a predicate P. So the predicate P is just some Boolean function of arity R, right? It operates on R variables, where each of these variables is in 0, 1. It then takes these variables and then maps them to a single Boolean output in 0, 1. So for instance, in the famous 3-sat CSP, this predicate P could just be, like the OR of 3 variables. In addition to the predicate, we then have the actual variables themselves. Today, I'm going to refer to the number of variables as n, and each of these n variables will just live in 0, 1. Next, we have the constraints themselves. And as I alluded to before, the way you get a constraint is you take the predicate, and then you apply it to an arbitrary set of R variables. Right, so here, the constraint C1, it just selects R of these variables from the universe of n variables and applies the predicate to this ordered set of R variables. And I'll denote the number of constraints by m. And lastly, just like in graphs, where edges can have weights, and these affect the cut sizes in the graph, in a CSP, you can also have weights for every constraint. And these just affect the value that the CSP takes. And then lastly, right, as in graphs where we're interested in cut sizes, and CSPs will be interested in something analogous, which is what we call the value that the CSP takes on a given assignment. And again, so if we denote an entire CSP by C, we can consider an assignment X to all of the n variables. We then let W of C of X denote the weight of all the constraints that are satisfied by X. Right, so recall every single constraint is just the predicate being applied to some subset of variables. And so when you specify a global constraint, you're also specifying the assignment to all the variables that participate in a given constraint. And then so either the constraint will evaluate to 1 or it will evaluate to 0. So 1 is what we consider for satisfaction of the constraint. Now, just like in graphs where we could define a cut sparsifier, this turns out to be enough to define a notion of CSP sparsification. Right, so again, we're given the CSP C, we're given this value of epsilon in 0, 1. We can then say that a sub-CSP, C hat, so this just means it's like a reweighted subset of the constraints. So we say that C hat is a 1 plus or minus epsilon sparsifier of C if for every assignment, simultaneously every single assignment, we have that the value of the assignment in C hat is within a 1 plus or minus epsilon factor of the value of the assignment in C. And so just like in graphs where the desire is to get very sparse graphs that preserve the cut structure, Here, the goal is to get sparse sub-CSPs that preserve the values of all assignments. And so the key question in this direction, as was first mentioned in the work of Kogan and Kraftgamer in 2015, asks, for a fixed predicate P, what is the smallest size as a function of the number of variables n and epsilon that every CSP with predicate P can be sparsified to? And so as an example of what a CSP sparsification problem might look like, I'll actually start off by showing you that cut sparsification can be viewed as a CSP sparsification problem. And specifically what my claim is that if you just consider the problem of 2 XOR CSP sparsification, right? That's to say CSP sparsification where your predicate P is just the XOR between two variables. This actually simulates or exactly captures cut sparsification in graphs. And so to see why this is the case, we can start by envisioning a graph here on the left, which I've denoted by G. And it's the same graph that we saw before. There's 6 vertices. And so in the correspondence between graphs and CSPs, we say that each one of the vertices corresponds with a variable in the CSP. And now for every edge in the graph, we add a corresponding constraint that touches the 2 corresponding variables. And so for instance, in this graph on the left, we have an edge between vertices 1 and 3. And so on the right, we have an XOR constraint between vertices, variables x1 and x3. And now the claim is that whenever you consider a cut in the graph on the left, this corresponds exactly with an assignment to the variables in the CSP. So as an example, if we just consider the cut S, which uses variables vertices 5 and 6, the corresponding assignment that we would look at is just the indicator vector for the set S, right? So that means that x5 and x6 would be set to equal 1, while all of the other variables would be set to be 0. And so if we look at this graphically, again, we have this set S, which contains vertices 5 and 6. And our claim is that an edge UV is cut by S if and only if the corresponding constraint evaluates to 1 when you're using assignment that's the indicator vector for S. And so it's a pretty intuitive statement if we just look at the picture, right? If you consider, for instance, the edge that goes between vertices, 2 and 6, this is a crossing edge, right? It goes from S to S bar, right? It leaves the set S. At the same time, when we consider the assignment, which is just the indicator vector of S, well then, variable x6 is set to be 1, variable x2 is set to be 0, and so the XOR between the 2 variables evaluates to 1. And in general, the XOR evaluates to 1 if and only if one variable is in the set S and one variable is not in the set S. And this is exactly the notion of an edge participating in the cut. And so it turns out that for this reason, sparsifying 2 XOR CSPs is exactly equivalent to cut sparsification. And so in this sense, this framework of CSP sparsification is a much more general object than just understanding cuts and graphs. So just as a couple of examples, right? So we just saw that when the predicate that you're looking at is the 2 XOR function, CSP sparsification is equivalent to graph sparsification. And so we know that you can get CSP sparsifiers of size O tilde n over epsilon squared. It turns out that in a separate work, we actually generalized this to show that when you just consider arbitrary arity XORs, right? So you're considering an XOR that's potentially on R variables, you can still get these CSP sparsifiers that are of size, again, O tilde n over epsilon squared. In a different line of work, people have studied hypergraph sparsification. And it turns out here the underlying predicate is something called the not all equal function. And so one way to talk about hypergraph sparsification, where we now know these near linear size hypergraph sparsifiers, is to say that for this R not all equal function, we indeed know CSP sparsifiers of size O tilde n over epsilon squared. And then lastly, kind of as a folklore result, it turns out that not every CSP can be sparsified. And indeed, if you just consider like the pretty simple predicate, which is an and of arity R, the best sparsifier sizes that you can hope for are in fact n to the R. And so in this sense, like for the and CSPs, there's a very strong sense in which sparsification is not possible. And then one thing that I want to point out about this is that most of these predicates that people study, or like people have studied in prior works, are typically symmetric predicates. And what this means is that the predicate itself, it doesn't really depend on the order of the variables that it's operating on. It just depends on the number of variables that are 0 versus the number of variables that are 1. And so with this, I can kind of informally describe what exactly we show in this work. And then in the next few slides, I'll actually dive into a little bit more detail and show exactly these dichotomies that we show for the sparsifiability of CSPs. And so first, our first contribution is to give a complete understanding of which symmetric predicates allow for linear size sparsification. And so just in the previous slide, we saw that this XOR functions, the not all equal function, do admit sparsifiers, while the AND function does not admit a sparsifier. And we actually give a very precise dichotomy theorem, which explains abstractly for all of these CSPs why this is the case. We then show a little bit more separate result, which is not strictly about symmetric predicates, but in fact for all predicates. We give an exact characterization of when predicates allow for any non-trivial sparsification. And so what I mean here is that, again, if we look at this AND of arity R, somehow a sparsifier size of n to the r is pretty trivial because the maximum number of constraints is in fact n to the r, right? There's n choose r possible subsets to operate on. And so it's natural to ask, when can you get any kind of compression at all, anything less than n to the r? And we show a very strong sense in which, there's some predicates which can get, non-trivial sparsification, while for others, it'll always be hopeless. And then lastly, as a kind of a consequence of all of these different frameworks that we show, we actually can derive an exact characterization of the sparsifiability of all predicates of arity 3, right, that operate on 3 variables. And so now I'll briefly talk about this first point on the characterization of the sparsifiability of symmetric CSPs. And so it turns out here that the classification of what makes a symmetric CSP sparsifiable deals with the levels of the predicate. And so the best way to understand this is with a picture. So on this left-hand column here, I've denoted by magnitude y. This is the, you could consider a predicate P, which is operating on some string of variables, which I've denoted by y. And now for every entry in this table, the way to understand it is that you're taking this predicate, for instance, the 2 XOR function, and you're applying it to a set of variables that has Hamming weight magnitude y. So for instance, when you take a 2 XOR function, and you're applying it to 2 variables, if the Hamming weight of those 2 variables is 0, well, then they both must be 0. And so the 2 XOR applied to 2 variables that are both 0 would equal 0. Now, when the Hamming weight of y is 1, it would mean that exactly one of these variables is 1. And so when you apply the 2 XOR to these variables, it'll evaluate to 1. And now you can continue on in this manner, right? So when the Hamming weight of magnitude y is 2, this means that there's 2 1s and everyone else is a 0. Then again, when you apply an XOR function to these variables, it will evaluate to 0. So in the 2 XOR column, I've kind of just truncated this after strings of Hamming weight 2. For the R XOR column, you can see this kind of alternating pattern where, the evaluation is just the parity of the number of ones in the string. So you get this alternation 0, 1, 0, 1, 0, 1, and so on. For the not all equal function, again, we're just testing, are all the variables the same or are they different? And this is somehow a generalization of hypergraph sparsification. And so here, when the Hamming weight of the string is 0, that means that all of the variables must equal 0. And so when you apply the predicate to a string like this, it'll, of course, then because they're all equal, it'll evaluate to 0, because it's the not all equal function. And now as soon as the Hamming weight is anything in the range 1 to r minus 1, it means that they can't all be the same symbol. And so the not all equal function evaluates to 1. And finally, when the Hamming weight of y approaches equals r, then the not all equal function will again return to equal 0. And you can do a same analysis for the arary and, where the only satisfying assignment is when everyone is 1, which is equivalent to the Hamming weight of y equaling r. And so the theorem, which I can now kind of say with this context of understanding symmetric predicates, is that for a symmetric predicate P, all CSPs with predicate P are sparsifiable to O tilde n over epsilon squared constraints if and only if the zero levels of P are periodic. Otherwise, there's kind of a dichotomy, which says that there are CSP instances that require quadratically many constraints. And so let me first explain what I mean by this periodicity of the zero levels. So again, the 2 XOR predicate is a predicate that allows for linear size sparsification. And so again, when we look at the levels of this predicate and we look at the zeros, we see that the zeros are periodic with period 2, right? Like the zero levels are exactly the levels that are, the even levels, when magnitude y is 0 or 2. And right, when you consider like the R XOR, again, you have this behavior where any even level of the predicate will have a 0. So in this sense, the zeros are very strongly periodic. When you look at the not all equal function, again, there's only 2 zeros in total. And so kind of this is trivially periodic, right? Like you could say that the zeros are periodic with period R because, level 0 is 0 and level R is 0. And then lastly, remember that the R array and is not sparsifiable to linear size. And so there should be a sense in which this is not periodic. And the way to understand this is that if you look at the first 2 levels of the predicate, when the Hamming weight of y is 0 and the Hamming weight of y is 1, it seems like the period should be 1, right? Because you have a difference of 1 between the 2 zeros. And so this should say, okay, well, that means everyone should be 0. But somehow you have a violation of this periodicity because when you finally get to magnitude y equaling r, like the rth level of this predicate, all of a sudden it turns into a 1. So in this sense, the 0 levels are not periodic because there's somewhere a violation of the periodicity. And so it turns out that this is exactly the reason why it's not sparsifiable. And in general, this works for any symmetric predicate. You can just do the simple test to check, is it are the zeros periodic or are they not? And then as before, I mentioned this second result, which characterizes exactly when non-trivial sparsification is possible. And so it turns out here, the characterization is even simpler. Again, so remember, you're having this predicate P of arity R. It turns out that all CSPs with predicate P are sparsifiable to, n to the r minus 1 constraints, or less than or equal to n to the r minus 1 constraints, if and only if the number of satisfying assignments to the predicate does not equal 1. And so essentially, if there's no satisfying assignments, if magnitude P inverse 1 equals 0, well, then it's just always unsatisfying. And so like any sparsifier is, it's just is trivial. So the way to really interpret this is that you need at least 2 satisfying assignments in order to get any kind of sparsification. And, any CSP is kind of trivially sparsifiable to order n to the r constraints, as I mentioned before. This is just because the total number of constraints to begin with is at most n choose r, or maybe n choose r times r factorial, all ways of choosing an ordered subset of r variables. And so in this sense, you get a very strict separation where either CSP requires n to the r constraints for any sparsifier, or you can always get a factor of n savings and get it down to O tilde n to the r minus 1. Lastly, I'll just mention as a corollary of these preceding theorems, it turns out we can get an exact characterization of which predicates of arity 3 are sparsifiable, or not really which are sparsifiable, but to what sizes they are sparsifiable. And I won't go too much into the weeds here, but it turns out that we show that CSPs with predicate P are sparsifiable to size basically n to the c, where c is in some sense the largest and that you can find within this predicate of arity 3. And I won't get in too much to the details here, but you should feel free to look at the paper to see an exact definition of what it means to find an and inside this predicate. And then lastly, I'll just briefly touch on some of the techniques that we use in this paper to derive these CSP sparsification results. And really the way you should interpret these is as some kind of generalization of this code sparsification technique that we introduced in a prior work. And so at a very high level, the way code sparsification works is that it takes any set of linear equations modulo a prime, and these are really, in a sense, constraints. Right? So you can imagine you have m equations where each equation is the form of some weighted sum of these variables xi, and we are testing whether or not it equals 0 modulo p. And so again, the variables are, again, you're just going to be x1 through xn. Each equation can have its own coefficients on this equation. And all you're testing is, does this weighted sum equal 0 mod p, or does it not equal 0 mod p? And so when it does not equal 0, this is what we call like the satisfying side of the constraint. And when it equals 0, this would be like an unsatisfied version of the constraint. And so in code sparsification, what we showed is that there exists a reweighted subset of basically O tilde n equations, where again, n here is the number of variables, x1 through xn, which for every assignment approximately preserves the weight of the satisfied equations, right? So if it's an unweighted case where every equation has weight 1, you're just approximately preserving like the number of satisfied equations. As an example, right, when p equals 2, each equation is just measuring, what is like the parity of this subset of variables that you're looking at. Does it equal 0 or does it equal 1? And so in this sense, code sparsification, when the prime p equals 2, is exactly just capturing like this XOR sparsification. And so in this work, we really consider two relaxations of the code sparsification framework. So the first is that we consider equations modulo non-primes. And even beyond that, we consider equations that are over arbitrary abelian groups. And again, the condition is we're still checking, does it equal 0 or does it not equal 0? It's just that we're allowing for the arithmetic to be done over richer structures. And the second relaxation is that we also look at higher degree polynomials. So in the previous slide, what we were really looking at was these linear equations. Now we actually consider like quadratic, cubic, and in general degree d equations over these arbitrary abelian groups. And so what we show is that where in the previous slide we saw these O tilde n size sparsifiers. Now we show there's these O tilde n to the d size sparsifiers, where d is going to be the degree of these polynomials that we're sparsifying. And so it turns out that this general framework is exactly what you need to show these results on like symmetric CSPs and arbitrary, like non-trivial sparsifiability. And I'll leave it there. Feel free to look at the paper for more details on how exactly this works, or feel free to reach out to ask any questions. Thank you.